You can see where it cuts. And this says that if you would get 100% test coverage, let's say 100% branch coverage, then you would detect these many faults. Assuming this linear relation holds. Now I ask a question. Do you think for very high coverage, this linear trend would hold? Or do you think you will see some bending, some saturation type of thing?
Yeah, because we usually have a problem like in coverage that there is dead code or invisible paths or something that we cannot actually test. So I feel like there would be like some going up, like more than.
So you think that this linear trend will not hold?
Not till the end, like to achieve like.
So do you think it will bend this way or that way?
It will go like that.
That will go like this?
Yeah, something.
So
no, this is coverage, so I'm thinking like in terms of time.
So you, okay.
Yeah.
So do you still think it would be like this?
Yeah, it will be like this. Yeah.
Okay.
This is coverage, not time.
Yeah, that's what most people think. Most people think that there should be some sort of saturation here.
Yeah.
But the problem with that is that if you assume that it is bending here, and you see that the coverage is increasing, but you're not finding more defects. And that would imply that in parts of the program which have not yet been covered, you're likely to find fewer defects than what you have found earlier.
Okay.
So that means in parts of the program which are harder to reach, you have fewer defects.
Okay.
So this would assume that you have fewer defects in parts not reached,
I guess we need
for which there is no justification.
We can plot like coverage with time, that would make more sense.
So one possibility is that it may go up like this, which cannot be ruled out logically, but then there is no logical explanation for this type of behavior. So I believe unless you do something that is, this is statistical, of course. So you can always construct an example by doing something which will be contrary to statistical expectation.
Counter example.
So, but statistically, I think you are going to find this behavior, and one problem is that there is not enough data that is available, but all the data that we have seen, it does fit this. And so so sometimes people ask this question. So sometimes there are some forums on the web, and that include some software testers. They said, I have this much fault coverage, and I have found so many defects. So what would be the total number of defects if I will get 100% fault coverage? And so a lot of people think that it would be linear, which is sort of true, but only as an approximation.
Right.
Because notice that behavior is not linear here,
Yeah.
but it would be linear only for a particular part. So in here, of course, there's the non-linear region, which is actually quite interesting. Now we have connected this to defect density, and basically the position of the knee. So this depends on initial defect density. So let us assume that you start testing some software which has already been tested somewhat. So basically your lower hanging fruit has already been picked. So you keep on testing, and lower hanging fruit has already been picked. So you will find almost nothing for lower coverage. And then when you will start finding defects, when they will start getting higher coverage, that's when you will start finding defects. That's what this knee implies. So if your defect density is lower, this knee will occur later. And if your defect density is higher, then the knee would occur earlier. Because that depends on how many of the low-hanging fruits you have already picked. Now there are some people who have worked on this related problems, and there are some papers that I have seen. There was a paper by Frankel and Iaquinono, and they did something, and we analyzed their work, and we have shown that their data is consistent with this model. There was another work done by Tom Williams, some analysis, and there was some work done by Peter Bishop in SafeCom 2002. So they came up with a similar model, an alternative to this model. And I think there are some Chinese people who have done some research, and they have come up with a somewhat different model, and then they compare that with this model. Any questions to comment? Any questions or comments? One question. So here, you could use any coverage measure to project the total number of defects. Which coverage measure should you use? Should you use an easy coverage measure or a harder coverage measure? And I think using a more strict coverage measure will probably give you better results.
In terms of its relationship to vulnerability?
In terms of predicting the total number of defects.
Oh, okay.
So the reason is that, notice that, let us say that if you get 100% coverage here, it corresponds to a certain number of defects here. But the model does not guarantee that 100% test coverage means 100% of the defects will be covered. But it only assures that this will be linear. So if you will use a more strict measure, for the more strict measure, the 100% coverage will be obtained later. And that will get you closer to the real estimate to the actual number of the number of remaining defects, or the total defects. Total defects means the ones you have found plus the ones that are presumably remaining. So in this case, let's say you have the data up to here, and this is your extrapolation. So this is the number of defects you have already found, and this is the number that you are projecting if you would keep testing and get 100% coverage. Now let me mention about something that you were mentioning, sort of related. It is possible that some part of the code can never be reached. Some part of the code could be dead code, which cannot be reached. So if you have some dead code, let us say you have 5% dead code. So let's say this is 100%, and this is 95%. So dead code you obviously cannot reach, and any defect that you have in the dead code is not going to bother you. So if you have some dead code, you should remove the dead code from the consideration. And this is, so let's say 5% of the code is dead code, then you don't need to worry about the dead code because it's unreachable anyway. Now you have to make sure it is truly unreachable, because you can have some code which is hard to reach, but it's still reachable. And you can have code that is hard to reach, and you will reach it only under some exceptional cases. But there is still code that sometime may get executed. So for example, if you have some exception handling routine, you want to make sure it works. So you cannot neglect a code that is reached only occasionally, but the dead code is the code that is truly dead. There's no way of getting to it anyway. Any questions or comments? Okay, next let us look at
The test.
oh, the test. Oh, sorry about that. Okay, it's time to give the test back.